Okay, so good afternoon guys. So, wala dapat tayong meeting ngayon kaso nag-request kayo na mag-meet tayo. So, ayun, masunurin naman ako. Sa lahat ng mga estudyante, kaya yata yung mga may gustong magklase. Anyway, before we start siguro dun sa actual na itatakal natin for the meeting, couple of announcements. So, if nabasa nyo na yung sa forum, for week 3, nagbukas ulit yung ating assessments. So, yung summative quiz tsaka yung coding exercise, pwede pa kayong mag-submit if gusto nyo. Sa mga may attempts na sa summative quiz, pwede kayong mag-re-attempt. Although hindi pa ako nag-check ulit as of right now. So, open yung assessments hanggang Friday, March 18, and I think 11 p.m. Yun. And ayun, another reminder na kailangan nyo ng 50% or 50 points per week. Yung ating summative quiz ay worth 80 points. And yung ating coding exercise ay worth 20 points. So if gusto nyo maka-achieve ng 50%, ayun, kaya mo nyo siya kahit sa summative quiz lang. And hindi na kailangan actually yung coding exercise. So yun ay kung nagmamadali tayo at gusto lang matapos yung course. And then, ayun, week 4, wala naman masyadong anything. Week 5 na actually na yun. Pero ayun, nasa week 3 pa rin yung iba. Well, ang week 5 naman ay, kung gusto nyo silipin, linear data structures. It's fairly simple. Ayun, linked lists and arrays. So, ginagamit nyo na siya since before, so it should be relatively easy for you to pick up. So ayun. And then lastly, we have released yung ating problem set. So 4 parts siya. 1 for the big O, 1 for recursion, 1 for linear data structures, and 1 part for non-linear data structures. Lahat sila ay worth 25 points. So in total, 100 points siya. And then, lahat to tentatively, well, medyo final naman na ang deadline nila is on Wednesday, April 27 ng 5 p.m. So, nilagay namin siya at Wednesday para hindi siya maging in conflict doon sa activities nyo for the week na due on Friday. And huwag mo kayo masyado mag-alala kasi from this week, dito yung bukas ng calendar. So, you have more than a month. So, March 17 pa lang. April 27 yung deadline. And for, I guess next week is your nonlinear data structures. And then yung week na to, March 28 to April 1, actually wala nang i-release na bagong materials, and that is just for your problem set. And then after that week, sa April, ayan. So ito yung prob set week nyo, yung March 28 to April 1, and then reading break, alam ko, yung April 4 to April 8, and then April 11 to April 15, Holy Week na yun. And after nun is graphs, yung April 18 to 22, and yung next week na yung deadline na talaga. So, ayun. So, you have 1 week na walang bagong materials for catching up and problem set. And then may reading break, may Holy Week, and then may week on graphs, and then tsaka magiging due yung ating problem set. So I hope naman that is enough time para magawa siya. So yun, hindi ko naman na dadaanan pa lahat ng mga problem set parts. Siguro we can set that to another meeting. So ayun, for today, ang ating focus ay ito. So meron tayong a small problem here na calculate the square of a given input n. So, and since ako yung gumawa ng problem, bawal ang multiplication division. So, ano ba yung point? Bakit magkakaroon ba tayo ng scenario kung saan bawal ang multiplication or division? So, sa lab kasi namin, UP Micro Lab, we are dealing with small computers. And sa isang simple na computer, kung isipin nyo, may logic gate or meron tayong, madali lang yung logic para gumawa ng adder or subtractor. Pero mahirap yung logic or mahirap gumawa ng set of logic gates na gagawa ng multiplier or ng divider. So, in a system na meron lang tayong addition and subtraction, minsan kailangan natin mag-rely on our algorithms para maka-accomplish ng mga very common na operations. Like for example, getting the square of an input n. So, kaya ako rin binabato yung mga ganitong types of problems para may encounter nyo din kasi siya pagdating nyo sa 153 or 143. Baka magamit nyo rin siya pag nasa microcontrollers na kayo. Although, yung more recent microcontrollers, meron na silang mga parang macros for multiplication. I think it's a fairly good exercise din para din ma-explore natin yung mga different ways of solving a problem. So, getting the square of an input n, pwede natin siyang tignan as counting the number of cells in an n by n na grid. So, if we have a 4 by 4 na grid dito, ang number of cells niya is nasa 16. So, yung first approach na titignan natin, which is yung simplest, is we just count each square. So, for example, kinol ko yung function square I na for yung input. Ito. So, i-highlight ko kung aling line basically yung dinadaanan natin. So, pagka-call ng function, we have an argument n, and masastore yun in memory para matandaan natin yung input na n ay 4. And then after nun, we have a temporary variable s na magsa-start at 0. And then another I na variable para doon sa counter ng first for loop. And then j yung counter ng second na for loop. And then mag-add lang tayo ng 1 for every iteration of for loop, which signifies yung pag-count natin ng isang cell. And then, ayun, after natin ma-add yung 1 dun sa S, mag-increment si J, and then we count another cell, so plus 1. So parang tuloy-tuloy lang yun hanggang mabuo natin yung isang row na maging J equals 3, S equals 4, and matatapos na yung loop ni J, babalik siya kay I, mag-increment si I, and then, ayun, babalik siya kay J, mag-add ulit ng isa pa, and then ng isa pa, ng isa pa, ng isa pa, and then umabot na si J sa 3, so mag-increment naman si I, and then mag-add lang, hanggang eventually umabot siya kay 16. So, na-count na natin lahat ng squares doon sa ating grid. So, kung nasusundan nyo, yung ing natin, it can simply or symbolize or represent yung ating rows and columns dun sa grid na binibilang natin. So dito I equals 0, j equals 3, siya yung cell na to. So index 0, tapos ay row 0, tapos column 3. Tapos pagdating natin ng I equals 1, j equals 0, yung row 1, and then column 0. So parang yun lang yung nire-represent niya. So, given this method or this solution, na-count naman natin lahat ng squares dun sa ating, lahat ng cells dun sa ating square of 4 and 16. Tama naman yung sagot. So, let's look at yung ating time complexity. Ayan, humihirap na. So, ayun, ako nga, ang preference ko, I start from the innermost na command or instruction. So, O of 1 siya. And then we repeat it in a loop for range n. So that is n times O of 1, so O of n. And then yun ay nire-repeat din natin n times pa. So we get n squared. So yung ating buong function na to is O of n squared. So dalawang nested na for loop na inulit natin n times, that is yun, n squared. Medyo mabagal siya actually. So let's have another approach na medyo mas mabilis. So alam naman natin na square siya. So yung kada row, alam natin we have n elements. So instead of isa-isa natin silang bilangin, magbilang tayo ng per row. So yung first row, and if we call square I2 of 4, so n equals 4, store natin yun dyan, and then s equals 0, and then for I in range n. So parang yung binibilang natin dito is per row. So sa 0th row, meron tayong 4 cells, so plus 4, and then sa next row, another 4, and then sa next row, another 4, and lastly, another 4. So we have a total of 16 na yun yung i-return na kay square I2. Now, looking at naman yung ating time complexity dito, O of 1 yung pag-add, and then ulitin natin siya n number of times. So, O of n. So yun, medyo straightforward. Wala pa naman nakakalito so far. Tama ba? If at this point, medyo nalilito na tayo, baka kailangan natin ng isa pang synchronization. Then, ito, I have what we call this lazy approach. So, what if we get yung square ni n minus 1, tapos mag-add ng 2n minus 1? So, ano itsura nun? So, pwede kong i-dissect yung single line na yun. So, kunin natin yung square I2 ni n minus 1. So, tamad yung function natin. Ayaw niya mag-compute ng square. So, uutusan niya yung isa pa nating function na kunin yung square nung n minus 1. So, ano mangyayari doon? So, if we call square L 4, pupunta dito, n equals 4. And then yung sa first line, it will call yung ating function kanina, si square I2. And, ayun, alam naman natin yung result dito. If n equals 3 over here, magre-return siya ng 9. So, yung 9 na yun, babalik siya dito. So, s is equal to 9. And yung 9 na yun, nire-represent niya yung square na to, or itong 9 cells na nandito. So, siya yung 3 squared. So, magdadagdag na lang tayo ng yung row sa baba, n, and then yung natitirang cells dito, 3 square. So, makukuha natin yung s na 16. So, nakuha natin yung square ng 16. So, gagana ba to if ginamit ko is n equals 5? So, makukuha natin yung square ni 4, which is 16. And then mag-a-add ng 5, 21. And then mag-a-add ng 4, 25. So yung square ng 5, tama din siya. So, ayan. So nasundan naman yung gustong gawin nitong function na to. So basically, in order to calculate n squared, we get n minus 1 squared and then add 2n minus 1. So nagmamatter ba? Kung nga ginamit ko dito is yung square I. So mag-work pa rin ba siya? Dapat mag-work siya kasi alam naman natin na si square I, tama naman yung i-return yan. I-return nito is, or yung itong line na to is equal to yung n minus 1. n minus 1 squared. So it doesn't matter kung ano yung function na ilagay natin dito as long as nire-return niya is n minus 1 squared. So that's something to take note of. Pero before tayo mag-proceed, syempre tingnan natin yung time complexity nito. So balik siya sa I2. So yung time complexity nitong dalawang addition sa baba is just constant. And ang time complexity naman nitong square I2 is yung time complexity ni square I2. Na, if you recall, nakuha natin na linear yung kanyang time complexity. So we can just replace yung TI2 dito with big O ni TI2 na n minus 1 yung input. And we get O of n. So actually, itong square L, wala tayong loops, wala tayong anything, puro assignment, puro addition. Pero since nag-call tayo ng ibang function, kailangan natin i-account for yung time complexity ng function na yun. So overall, ang time complexity pa rin ni square L ay O of n. So ayun nga. It doesn't matter kung ano yung ilagay natin dito as long as nire-return niya yung square ng n-1. So what if itong function natin, it calculates the square of n? What if we use the function itself? So doon pumapasok yung pagiging recursive. So notice yung difference here. Yung sa kanina, ang ginawa natin ay another function na nagka-calculate ng square yung gamit. But in a recursive function, gagamitin mo yung sarili nating function. So, ayun. So, nakita naman yung transition. So, bakit may plus n minus 1 dito is para ma-complete yung square na mas malaki, di ba? So, ayun, if we try simulating yung pag-run nito, when we call yung square r ng 4, pupunta siya dito. And then, first, ika-calculate niya yung square r ni n-1. And that will look like yung pag-call nito. And then, this one in turn, yung n niya is 3 na instead na 4. And then, tatawagin niya ulit si square r n-1. And then, tatawagin niya ulit si square n-1. So, naging 3, 2, 1. And, well, parang may problem ata tayo. Parang hindi na nagkakasya sa slide. If ituloy pa natin, diba? Makukuha natin na eventually magiging n equals 0, pero parang tuloy-tuloy pa rin siya. So, square n-1. So, may n-1 dito. And, okay, napuno na yung slide. And ito yung tinatawag natin na stack overflow. Kasi wala na tayong space. Ano natin lalagay yung susunod na call? So, ayan. So, one important thing for recursive functions ay yung tinatawag natin na base case para tumigil yung pag-call natin ng pag-call. So, in this case, so instead na, ayun, napuno yung screen natin, let's try it. Ayun. So, meron lang tayong extra step. So, chine-check natin if n equals 1. Otherwise, ayun, proceed tayo with the recursive call. And then, ayun, we have the recursive call here. N equals 3 now. And then, ayun, n is not equal to 1. So, tuloy pa rin, recursion. Tuloy ang recursion. Next step, n equals 2. N is not equal to 1. So, proceed pa rin doon sa recursive call. So, ayun, medyo nasisikipan na pero kasya pa rin, manageable. So, ayun. If we get yung sa next line, ayun, n is now equal to 1. So, we can go back dito sa return 1. And, ayun, ka-return ni 1, we basically replace yung kaninang call with yung return value na 1. And we actually counted yung square ng 1, which is 1. 1 squared is 1. So, si 1, dadagdagan natin for this call, dadagdagan natin siya ng 2. And dadagdagan natin siya ng 1. So, yun yung tatlong squares dito. And ang i-return nito is 4. So, 4 yung babalik dito sa earlier case natin. So, si 4, ma-add with n plus n. But this time, si n ay equal na kay 3. So, ma-add yung dalawa. Yung 3 dito and yung 2 dito. And then ayun, this is equal to 9. And then eventually, babalik tayo dun sa original na function na nag-call. We have 9 plus n minus 1, where n is equal to 4. So, nakompleto na natin yung buong square and nabilang natin na 16 yung squares pagka ang n natin ay 4. So, nasundan ba yung pag ano natin dun sa recursion dun. Yes. May mga nagta-thumbs up. Okay. So, comparing it with our lazy approach kanina, halos pareho lang sila, di ba? So, ayun, yung functions natin dito, they return the same thing, but through different means. So, ayun, hopefully, this demystifies yung paggamit natin ng recursion para maintindihan niyo siya ng slide. So, kung ito lang yung naka-define natin, paano tayo magiging sure na tama yung i-return nito? Kasi siya lang yun nandyan eh. Kung dito sa case kanina, di ba, meron tayong another function na siya yung, sa kanya tayo nagre-rely dun sa sagot. Now, it just relies on itself. So how do we know if this returns the correct value? So doon actually pumapasok yung base case. Alam natin na pag tinawag natin si square 1, tama siya. Kasi hard-coded yon. If n equals 1, return 1. Alam natin na 1 squared equals 1. Now that we know square 1 is correct, pag tinawag natin si square 2, that is square 1 plus n minus 1. So that is 1 plus 2 plus 2 minus 1. So 4. So correct siya. If we know square 1 is correct, wala ako sa transitions. We know square 2 is correct. If we know square 2 is correct, we know square 3 should be correct. And then kung tama si square 3, tama dapat si square 4. And so on and so forth hanggang makarating dun sa gusto natin makuha na square. So this is what we call, or this is similar to what we call proof by induction, na assuming na tama yung previous step, kailangan lang natin masabi na totoo yung next step. So, assuming na tama si square 3, we just have to make sure na tama si square 4. So si square 3 is plus 2n minus 1 ni. Ay, pag nag-plus 2n minus 1 tayo kay square 3, makukuha natin si square 4. And if we prove na tama siya for one case, or the base case, parang magkakaroon ng ripple effect na magiging tama na lahat ng iba. So, I guess yun yung parang key thing when it comes to recursion. So, ayun. Okay, medyo may tiwala na tayo na gumagana yung function. Paano naman yung time complexity? So, I guess yun naman talaga yung focus ng ating course. So, lahat ng slides so far, supposedly, well, ako, originally, inassume ko na daanan nyo in 1-1-1. Pero siguro yun, medyo nasa latter part ng 1-1-1 siya. Baka hindi na kayo masyadong nakikinig by then. Pero either way, baka makalimutin lang kayo. That's okay. What's important is, ngayon, at least sana naintindihan mo siya. Pero yun, for the actual point of EEE 121, we get the time complexity of this function. So recall na yung nung kinuha natin yung time complexity ni yung lazy approach. So basically, in-add lang natin yung time complexity ng function na kinol natin, di ba? So lahat ng other functions, ay lahat ng ibang commands, addition, assignment, O of 1, and in-add natin yung time complexity ng hiniram natin na function or yung inutusan natin na function din sa loob. So ganun din siya for recursive functions. So for recursive functions, we get, well, yung other parts muna. So yung pag-check ng if statement is O of 1, and if true, O of 1 lang siya. However, if hindi siya true, pupunta tayo dito sa return statement na to. And yung return statement ay, a t of n minus 1 na operation, and then an O of 1 to add n, another O of 1 to add another n, and then another O of 1 to subtract 1. So, ang ating time complexity, may dalawang case siya. If ever true, si n equals 1, and if ever false siya. So, if ever true siya, we get T of n equals O of 1. If ever n is greater than or not equal to 1, T of n is equal to T of n minus 1 plus O of 1. And ito yung tinatawag natin na recurrence relation na nandun sa materials na nasa UVLE. So, ayan, yung recurrence relation, so yung time it takes for square of n is the time it takes for square of n minus 1 plus other operations. And, ayun, rewrite ko lang in fancy font na pang formulas. So, T of n is equal to T of n minus 1 plus O of 1. Yun, we can use substitution. So, hopefully, if hindi nyo man siya na-gets before, ngayon may konting background, na-gets nyo paano siya or ano nangyayari. So, we just try and expand and see a pattern. So, from T of n minus 1 plus O of 1, magiging T of n minus 2 plus 2 times O of 1. And then T of n of 3 plus 3 times O of 1. And, ayun, eventually, kung ano yung isosubtract ko kay n dito sa loob, siya yung minumultiply ko kay k. And, ayun, if I let n minus k equals 1, or k equals n minus 1, pag sinubstitute ko tong n minus k dito, magiging 1 siya. And yung k naman na nandito is magiging n minus 1 siya. So, T of 1 plus n of 1 times O of 1. So, si T of 1, we already defined it as T of. So, T of 1 is O of 1 pag n equals 1, di ba? So, T of 1 dito is, ayan, this one is constant and this one is n times constant. So, ang largest growing term natin is O of n. So, yung substitution parang medyo blind siya to what's actually happening. It's purely mathematical, di ba? So, hindi natin kailangan intindihin kung anong ginagawa nito. And basta algebraically, totoo lahat ng ginagawa mo, you're on the right path. So, if you're more visual or mas gusto mo ng may ibig sabihin yung mga steps natin dito, we use the recursion tree approach, which is yung actually yung mas preferred ko rin. So sa recursion tree, ayun, i-expand mo si T of n minus 1 to its yung equivalent. So T of n minus 1 is equal to T of n minus 2 plus O of 1. And then si T of n minus 2, i-call niya si T of n minus 3 plus O of 1. So you can say na this one, siguro I can annotate din to. So, for example, this is yung square ni 4. And tinawag niya si square ni 3. And then tinawag ni square ni 3 si square ni 2. So, parang expand lang tayo ng expand hanggang makarating tayo dun sa dulo na square of 1. Hanggang umating siya sa point na kinukuha natin yung T of 1. So, ano naman yung mga total na ginawa natin na operations? So, effectively, yung mga T terms na nandito, in-expand natin sila. So, parang hindi na natin sila kailangan bilangin. So, baka mag-double count. So, parang burahin mo to. Burahin mo to. And kailangan mo lang i-add lahat ng mga O of 1 terms na natira dyan. So, ano ba yung nasa susunod na slides? So, yun, paano bilangin lahat ng nandyan? Kailangan natin alamin kung ilang levels ba lahat to. So, paano malaman kung ilang levels? Ayun, nag-start ka with T of n minus 1 and eventually naging T of 1 siya. So, you can expect na kung level 4 to, nag-subtract ka ako ng 1 at a time, ilang levels lahat yun? So, 4 levels bago siya makarating kay Actually, 3 levels lang pala bago siya makarating kay T of 1. If I have n equals 100, I am sure na meron akong mga 99 steps bago makarating kay T of 1. So actually, this is n minus 1 levels. Pero kung naka-big O naman tayo, so if we plus or minus something kay n, hindi masyado nagmamatter. So yun, if we have n levels, we have T of n is equal to n times O of 1. Pakitabi na lang ng ulo. And stretching. So we have yung ating time complexity na O of n. Then you can also imagine, ano naman, if we get square of 4, we have square of 3, then 2, square of 2, square of 1. So parang apat na functions yun. So if we get square of 100, meron tayong square of 99, 98, 97 hanggang 100. And kailangan ko lang i-add yung time complexities ng lahat na yun. Fortunately, in this case, O of 1 lahat nung ina-add natin. So medyo madali silang kuhanan ng sum. Pero pagdating dun sa mga examples na nasa week 3, hindi lang siya simpleng O of 1. I-expect natin tingnan later on. Pero hopefully, nakukuha niyo yung gist nung gustong gawin ng recursion tree. So basically, lahat ng mga function calls is pina-plot out natin yung kanilang mga gustong gawin. Now, in terms of memory naman, parang similar lang din. Parang yung memory ng ating function is yung memory nung ginagamit nung nasa loob. And if we have another function, we have to account for yung memory ng function na yun. So ayun, kamukha lang niya yung kanina. So eventually, makukuha nyo rin dito. So eventually, makukuha nyo rin dito is ang ating M of n ay O of n. So ayun, so yung first big question dito, what if meron akong array dito na 1 times n. So basically, n elements na temporary na list. So wag niyo munang, basically theoretical lang to, no? So parang wala naman talaga siyang point. Pero in this case, we are using O of n na space for each function call. So yung recursion tree natin, imbis na puro O of 1 yun nandyan, magiging O of n, and then O of n minus 1, minus 2, and minus 3. Tapos eventually, pag in-add mo yan, ito yung summation niya. So starting with k equals 0, O of n, and then minus 1, minus 2, minus 3, hanggang eventually umabot ka kay last level or D. And ayun, if itong expression na to, if gusto mong makuha yung closed form na solution, so if familiar ka sa mga sequences, arithmetic series, that is n plus n minus d times d over 2. So yung kailangan na lang dito is makuha yung number of levels, d. Nakuha naman natin yung kanina. It's around n or n minus 1. So if i-replace natin si d with n, we get n plus n minus n times n over 2. So that is n squared over 2. So, ayun, if meron tayong n memory na ginagamit per function call, we eventually get an n squared na result. So, kung titignan nyo rin kasi, if si square of 4, gumamit siya ng 4 memory, si square of 3, gagamit siya ng 3 na memory. And then, yung susunod, gagamit siya ng 2 na memory. And then, yung last, gagamit siya ng 1 na memory. So, if mag-add up, that will be equal to 15 or 4 squared minus 1. Okay. 4 plus anyway, and then over 2. 7, 8, 9. So you get the point, right? If we have square of 100, that is 100 units of memory plus 99 units of memory plus 98 units of memory plus 97, 96, and so on and so forth. And nakukuha yung sum nun is 101 times 50 over 2. And then 101 times 50. So 5,000 memory units. So basically, yun yung sa recursion tree. It's yung dati, pag iteration, nagmumultiply lang tayo, di ba? And pwede naman natin i-tabulate per iteration ano yung kailangan. So dito sa recursion, tinatabulate lang natin per recursion kung ano yung kailangan natin. So hopefully makita niyo yung parang parallel na yun para hindi kayo masyadong mahirapan sa kanya. So yun, moving on, we have another approach which is yung divide and conquer. Na instead of going one level below, so kung si square of 4, kukunin is square of 3, what if we half it? Para kung square of 100, kailangan lang natin si square of 50 instead of square 99. So, and if we get n over 2 squared, kailangan lang natin siyang i-multiply 4 times para makuha si n squared, di ba? Nakuha naman yun. So, if we get yung square ni n over 2, so, ayun, remember lang na yung bit shift to the right is integer division by 2. So, ayun, going back, yung point natin, di ba, is we're using a simple computer without multiplication and division operations. Pero madali lang mag-shift ng number of bits. Kasi parang maggagalaw ka lang ng wires na bit shift mo na siya, di ba? So, ayan. We can easily implement yung bit shift. And yung bit shift to the right ng 1 is integer division by 2. So if we run this for square 4, we get na. Ayan, n equals 4. So umpisa, check if n equals 1. And then hindi siya equal. So we get S4. And si S4, makakalculate natin with square DNC. And bit shifted to the right ng 1, which is 2. So ito naman, ayan, pag n equals 1, not really, it's n equals 2. So, i-run natin ulit yung recursive na call. And, ayan, we get square DNC na n equals 1 this time kasi na-bit shift to 2. And if n equals 1, we return 1. So, that is yung ating first square dito na babalik kay square 2. Square DNC 2. And si S4 equal na siya kay 1. And ilang lang natin siya i-add 4 times. So, 1, 2, 3, 4. So, we have our square over here. And then, kakuha natin ito. That is 1 plus 1 plus 1 plus 1. That is 4. So, yung babalik na S4 dito is equal to 4. And then, kailangan lang natin siyang i-add 4 times para mabuo yung buong square. So, yan. Nakuha natin si 16. So, yan. Meron ba kayo nakikitang problems sa approach na to? Wala ba? Kaya natin maging interactive dito, guys. Wala kayong nakikitang problem sa approach. Ayun. Okay, so may nagsabi in a direct message, what if odd number yung input natin? So let's say 5. So we need to count yung 25, di ba? So, applying our same algorithm, ayan, pag si 5 shift natin to the right, makuha natin is still 2. And alam naman na natin siguro yung result nito is eventually magiging 4. And pag times 4 natin is ito lang yung makukuha natin. So meron tayong kulang dito. So anong gagawin natin? Iyak. We can add some form of compensation pag add number yung ating result. So yun nga, hindi siya tama. Lagay tayo ng konting compensation. If n is odd, dadagdag natin yung kulang. So, ayun, if we run this one, ayun, pag n is odd yun nga, mag-add tayo ng n plus n minus 1 kasi nawala yung isa doon, diba? So, ayun, going through the motions, 5 with shift to the right is 2. Mag-run to and get 1. And then n is even, so just return S4. So, pagdating si S4 dito, S4 plus 4 ay S4, isang S4 to, isang S4 to, another S4, another S4. And then, ayun, S4 equals 16. And if we check, yung n natin is odd, we just add 5 and 4, or 5 minus 1. And makukuha na natin yung buong list natin na may equal siya. Or may makukuha na natin yung buong square ng 5, which is 25. So, ayun, mukha ba siyang convincing enough ba sa inyo na tama siya? So essentially, ang alam natin makukuha natin dito is square of 4. Since alam na natin, or pwede kayong parang mutual recursion. Tawagan nyo si yung nauna recursive function natin. Ano ba yun? This one. And then pag odd siya, gagawin nyo yung, ay pag odd, gagawin mo to. Pag even, gagawin mo yung kanina. Well, yung simpler case naman is outright ng ilagay na lang yun for odd operations dito. Okay. So yun, if hindi kayo masyado convinced na gumagana siya, well, I think naka-open siya somewhere. Sana na lang wala akong napakita. Hindi dapat. Dito pala. So, I have yung codes here. So, DMC. Ito yung naunang DMC na walang compensation for odd numbers. And then this one is may compensation for odd numbers. So, so, ayun, yung file na to is named square.py. So, if I run in interactive mode, yung file, I should be able to call the function. And we get 10,000. If we get 13 squared, not 69. So 16 squared is 256. 25 squared is 625. So, mukha naman tama. Well, yung pag-verify na kung tama talaga siya is nasa latter part pa ng course, which is called algorithm correctness. Pero for now, ayan, mag-test lang tayo for a few values. Pag tama, edi tama. Ganun din naman yung coding exercise natin. Pag tumama siya sa mga test cases, tama siya. So, ayan, going back, paano yung time complexity naman ng function na ito? So, ayun, labelan ko na lahat ng alam na dapat natin. So, lahat ng hindi square, DNC2, ay constant operation. So, ito kahit nag-add tayo ng 4, you can say na O of 4, pero that's still O of 1. So, ayun, ano yung time complexity nito? It's T of n, pero si n is divided by 2. So with this, ito yung makukuha nating recurrent solution. If T of n, where n, if n equals 1, it's basically O of 1. If T of n, or if n is greater than 1, it's T of n over 2 plus 1. So may difference ba if odd or even si n? So, difference of plus O of 2. So it's, and we can also consider yung worst case na laging odd yung result. So pwede naman T of n over 2 pa rin siya plus O of 3. Pero same lang naman siya. So we get T of n is equal to T of n over 2 plus O of 1 pag greater than 1 and O of 1 if n equals 1. Ngayon, if na-encounter nyo na yung master theorem, mabilis lang to. By master theorem, yung A nito equals 1, B equals 2, and F of n equals O of 1. Then kunin lang natin si n to the log B of A. So that is n log 2 of 1, which is n of 0, which is 1. So it is comparing yung n log term with our f of n na O of 1 equals sila, pareho constant. Therefore, ang ating theta or big O and omega is n, yung n log na term times log n. And since yung n log term is 1, our time complexity is log of n. So usually, pagka big O or theta or omega yung pinag-uusapan, it's log without the O to say na it doesn't matter kung ano yung base. Yeah, kung base 10 or base 2 siya or base E. So yun, pwede natin tingnan yung ating recursion tree for this one. So si T of n over 2, we'll call T of n over 4. Si n over 4 maging n over 8, etc. and etc. So parang ganun din, ina-add lang natin lahat ng O of 1. Pero yung difference natin dito, instead of mag-subtract ng 1 kay n, is hinahati natin siya. So eventually, pag hinati natin si n enough, may equal siya kay 1. So n over 2 to the times na hinati natin siya, naging equal kay 1. So yun yung depth or number of levels. So for example, if n equals 4, pag divide natin siya by 2 to the 2, may equal siya kay 1. So tama naman, pag si n dinivide mo by 2, maging 2. So ba't ko na? Pag si 4, dinivide ko by 2, equal siya kay 2. And then if you divide ko it by 2, may equal siya kay 1. So ilang beses ko dinivide si 4? 2 times. If nasa 16 ako, divide by 2, that is 8. And then divide by 2 ulit, that is 4. Divide by 2, that is 2. Divide by 2, that is 1. So, ilang times natin siya dinivide? 4 times. So, 2 to the 4 times natin siya dinivide. I mean, 4 times natin siya dinivide, 2 to the 4 is 16. So, kaya 2 to the depth, n over 2 to the depth, approximately 1. Kasi pag ginawa natin itong 17, ganun din yung number of divisions natin. So meron din other approaches para makuha yung depth. Pero for me, yun yung medyo intuitive. Pag n over 2 to the depth. So what if gawin ko tong n over 3, n over 9, n over 27. So mangyayari lang dito, maging 3 to the depth siya instead na 2. Kasi pag dinivide natin siya, always by powers of 3. Yung kanina, always by powers of 2. So yun, proceeding. So ibig sabihin yung depth natin equals log n, and depth yung number of levels natin. So depth times O of 1 is yung ating total running time. And ang ating time complexity therefore ay, well, log of n times O of 1 and eventually O of log n. So, ayun. Pwede nyo gamitin yung substitution method if you wish, and you should get the same answer. So, ayun. Ano pa ba nandito sa slides? So, what about yung memory ng ating function na ito? So, ayun, similarly kanina, we just incorporate yung same recurrence relation, pero this time, memory yung tinitingnan. And parang pareho lang naman, yung memory nito is yung memory nung kinonsume, nung kinol natin siya na n over 2 yung naman. So, pareho lang yun. Makuha natin result na O of log n. However, let's make it more complicated, I suppose. What if apat na beses ko tinawag si square instead of adding it 4 times? So, yung sa time, apat na yung t of n over 2 na terms natin dito. So, yung recurrence relation natin is 4 times t of n over 2 plus O of 1. And if we use the master theorem, a equals 4, b equals 2, f of n equals O of 1. If hindi ka nakaka-relate, basahin mo na yung material natin for week 4. Kasi ang laki na natitipid nating oras doon. So, yung n log term is n log base 2 of 4, and that is n squared. Then, if we compare n squared to f of n, it is much greater than O of 1. So, ang ating time complexity is yung n log na term, which is O or theta of n squared. So, ayun, yung big theta nga is either big O or big omega. Pero, ayun, so, O of n squared siya, pareho lang naman yung point natin dito, di ba? Dun sa nauna. Bakit ang laki ng difference? So, from O of log n, naging O of n squared tayo. Parang ang lala, di ba? So, that is because kada recursive call natin dito, magsuspawn siya ng sobrang dami pang recursive call. Parang nag-nest siya eh. So, if we look at the recursion tree, so dito na yung medyo naging murky na pagdating sa notebook. Kasi yun nga, apat yung t of n over 2 terms, so apat yung expansion natin dyan. And then yung kada apat na in-expand natin, mag-expand to apat. So yung initial na times 4, naging times 16, tapos magiging times 64, etc. etc. So parang sobrang dami na ng dilito sa recursion tree natin. Hindi na siya iisang branch. So, since pare-pareho lang naman yung value ng mga yan, ba't ko pa siya kailangan ulitin? Ba't di ko na lang add ng diretsyo? So, ayun. Siguro, this just further says na if dumami yung recursive calls natin, pagdagdagan pa natin yung recursive calls natin dyan, lalala ng lalala yung ating time complexity. So, siguro, if we have a recursive algorithm na madaming recursive function call, pag kaya nating bawasan yung mga recursive na function call, it will certainly improve yung ating time complexity. Pero yun, since kaya rin naman dapat natin makuha yung time complexity given the recursion tree, tuloy lang natin to. Kahit mahirap. So, we can tabulate yung number of nodes natin or number of O of 1s per level. So, at level 0 or your initial call, we have 1 O of 1. At level 1, so after 1 recursion, we have 1, 2, 3, 4 levels. And then after nito is 16 na O of 1. And then 64 na O of 1 yung susunod. And so on and so forth. Hanggang umabot siya dun sa last level na D. And then yung total number of O of 1s natin should be approximately 4 to the D. So, paano natin nakuha yung 4 to the D? Kasi, isipin nyo, so dito, this is 4 raised to 0, and then this is 4 raised to 1, 4 raised to 2, and 4 raised to 4. Yung next level is 4 times no previous level. So that is 4 to the 5th power in level 5. So on level D, we have 4 to the D na levels. Okay? And, ayun. Ito. So, yung makukuha natin, yung total natin na makukuha per level, pag
inad natin lahat isa-isa is yung summation expression na from k equals 0 to d ng 4 theta k. And if familiar kayo sa mga geometric series, this simplifies to 1 minus 4 to the d plus 1 over 1 minus 4, or ito, 4 times 2 to the d times 2 to the d minus 1 over 3. So, you'll know bakit ko hiniwalay ito dalawang 2 to the d instead na isang 4 to the d later on. So, ang goal naman natin ngayon is mahanap kung ano yung value ni d. And similarly, sa kanina, pareho yung recursive call natin, di ba? N over 2. So, you'd expect na, kuwari, takpan natin lahat ng, kuwari, wala yung tatlong terms dito. Alam natin na magre-recursion to hanggang log of n na levels, di ba? So, pag tinanggal ko kasi yung tatlo dito, it's as if tinanggal natin lahat ng mga nandito pa na nasa right side nito. So, isang term lang yung kinukuha natin. And, ayun, yung ating tree will have the same depth pa rin kasi same lang naman yung ginagawa natin sa input. Hina-half natin siya every time. So, kung hina-half natin siya every time, ilang levels yung kaya natin magawa, ganun pa rin siya. So, yung levels ay, ayun, n over 2 to the d, approximately 1. So, yung levels natin, or yung d, is log n. Pero, and we can keep it at 2 to the d equals n. Para kaya natin i-substitute dito, yung 2 to the d na terms, magiging n terms. So, we have 4n squared minus 1 all over 3. And pag kinuha mo yung big O, it's O of n squared. So, ayun. So, yung medyo may konting jump lang is yung pagkuha ng number of levels. Pero similar lang yung pagkuha ng number of levels as if isa lang yung recursive call. So, ayun. So, we get na O of n squared siya. So, paano naman yung memory natin? So, ayun. So, basically, naging m of n yung mga nandito. Pero, mag-add up ba yung memory consumption ng ating mga recursive call? So, one thing to note about memory, unlike time, memory can be returned. So, yung oras, hindi siya mababalik, pero yung memory, kaya mo siyang ibalik. Well, merong mga memories na gusto mong kalimutan, pero, di ba, bumabalik. Okay, kumari wala akong joke. Ayun, pagka kasi, consider natin, kumari, square of 4, kukall niya si square of 3, na i-call, ay, si square of 4, kukall niya si square of 2, kukall niya si square of 1. Pagkatapos ni square of 1, ibabalik na ni square of 1 yung ginamit niya na memory. And pagtapos na si square of 2, babalik niya na yung ginamit niya na memory. So the next time na magkukall tayo ng other function, yung memory natin, nandun na siya sa what it was before, basically. So basically, yung ginamit na memory nito is nabalik niya na kay dito, and pwedeng yun na yung gamitin na memory nitong next step. So actually, yung memory consumption ng multiple recursive calls, hindi sila nagpapatong-patong. Kasi one of a time lang sila mag-run. Unless parallelized yung computer nyo, madaming multiple core. Pero assuming na single core lang tayo, kasi sumihirap yung usapan pag pumasok tayo doon. Assuming na isang core lang and isang function lang yung mag-matter at a time, so yung memory consumption natin, similar siya dun sa initial case na isang call lang ng m of n yung ginagamit. So, yung memory consumption natin is still O of log n. Kahit na yung ating time complexity ay O of n squared na. So, in summary, yung recursive functions natin
in order to understand them, parang meron tayong tinatawag na leap of faith. So hindi ko original yan. May napanood lang din ako ng video on recursion na ganyan yung tawag niya. A recursive leap of faith. So kailangan nating maniwala na yung previous call natin dun sa recursive function ay totoo. And assuming na totoo yun, mas madali na sa atin makuha yung totoo ngayon. So basically, kung alam mo yung square ni 3, madali lang makuha yung square ni 4 kasi mag-a-add ka lang ng 2n minus 1. Or, dun sa example, sa activities, or dun sa material, pag alam na natin yung factorial ni 3, mag-multiply lang ako ng 4, makukuha ko na yung factorial ni 4. And for example, then, sa merge sort, papasok ko yung merge sort. Pinakamabilis siya mag-open sa akin dito sa HackMD. So, kahit na hindi mag-run yung Python code, dito ako pupunta. So, sa merge sort, di ba meron tayong dalawang recursive call dito? Merge sort. So, sinort natin si left and sinort natin si right. So, assuming na sorted na si left and assuming na sorted na si right, mas madali na tayong mag-merge, di ba? Kasi kukunin mo lang yung initial na element. Kasi for example, meron tayong dalawang list na hindi natin minerge, ay hindi natin sinort muna, mas mahirap siyang i-merge into a sorted na list. So basically, yun yung gustong gawin ni recursion. Assuming na meron ng totoo, or meron ng na-solve na smaller problem, paano mo solve yung bigger problem? And most of the time, mas madali na yun for you. So kung alam mo na sorted na yung dalawang list, mas madali na siyang i-merge for you. Initially, if hindi mo alam na na-sort yung dalawang list, mas mahirap sila i-merge. So yun yung parang premise ng merge sort. And same with dun sa maximum sub-array na problem. Nahanap mo na yung maximum sub-array sa kanan, nahanap mo na yung maximum sub-array sa kaliwa. So you're sure if meron pang ibang maximum sub-array, mag-occur siya dapat sa gitna. Kasi if hindi siya nag-occur sa gitna, kunwari hindi kasama yung nandito, kunwari ito pala yung maximum sub-array natin, makukuha na natin siya dito. Dapat, di ba? So, na-solve na dapat siya. So, meron na tayong additional assumptions for our middle na algorithm that will make it easier for us, or that will make it faster dun sa ating algorithm. By knowing na hindi ko na kailangan problemahin kung nandito lang siya. Hindi ko na kailangan problemahin kung nandito lang siya. Ang problema ko na lang is if nandito siya sa gitna. Kasi yung nasa kaliwa and yung nasa kanan, na-solve ko na. Paano ko siya sinolve? Gamit yung sarili kong function or sarili kong definition. Kasi magawa siya. So basically, ganun yung ating point for recursion. Then, recursion or recursive time complexity starts with the recurrence relation na kaya mong makuha using your original methods sa pagkuha ng time complexity. So, di ba, yung sa time complexity, bibilangin natin lahat ng mga time complexities na nasa loob ng function. And basically, for recursive functions, hindi mo lang siya isi-simplify agad. Magmumukha lang siyang t of something na term. T of n over 2, t of n minus 1, t of n minus 2. So, and then, makakuha ka ng tinatawag natin na recurrence relation na pwede mong i-simplify through different means para makuha yung actual na time complexity. Pero ang point lang naman ng pag-simplify ng time complexity is parang ine-expand mo lang or gusto mo lang makuha saan ba talaga equal to if in-expand ko pa siya. And saan ba equal yan pag in-expand ko pa siya. And so on and so forth. And kung nga, kung ginamit ka ng recursion tree,
ayan, magkakaroon ka ng medyo mga complicated na mga summations. But essentially, ang point lang nun is nagbibilang lang tayo ng number of occurrences. Then lastly, for space complexity, we only consider one path of the recurrence tree. Kasi yung memory natin nababalik. So, kung titignan mo yung tree dito, yung wala pang kalat, ayan. Yung memory na kailangan mo dito ay, I guess yung memory nito, mag-a-add sa memory nito, and then memory nito, and then memory nito. Pero pag tapos na to, at bumalik ka dito, at nag-run ka ulit ng isa pang function, eh yung memory mo is parang nasa same level pa rin as before. Hindi na siya dumagdag kahit na meron ng ibang nag-run before it. So essentially, pag natapos na yung function na to, mawawala na yung, or ma-free up na yung memory na ginamit niya. Ibabalik niya na siya, and pwede na siyang gamitin ng susunod. So essentially, kailangan lang natin i-consider for memory is yung summation from one recursive call to its deepest na level na gano'n. So yun lang naman yung gusto kong sabihin dun sa mga materials. So I guess ito is a much more expanded or slower version ng notebook kasi medyo limited yung time. But essentially yun. Ito na yung summary ng for week 3 essentially. And yung week 4 naman kasi, ganito lang din naman siya. Except that may specific lang na form yung ating mga functions. Meron lang ay yung n over 2 siya parati. So, ayun, I guess that is the end of the presentation. 266 slides.
Ayun, hopefully this was helpful with regards to yung pag-catch up for the week 3 and week 4 exercises. Ayun, yun nga, napag-usapan naming handlers. Madami rin nag-bring up, madami daw na-relate. So, inopen namin ulit yung week 3 na assessments. Pero hindi kami nag-adjust ng deadlines for week 4. So, ayun lang. So, kailangan yung i-manage, I guess, yung time nyo. If, for example, yun nga, 80% to, 20% to, kayo na mag-decide kung ano yung mas importante, I suppose. And, ayun, are there questions as of now? Okay, so may nagtanong, siguro i-bring up ko na lang din sa notepad para for the benefit of everyone. Ay, so, sabihin ko na. So for microcomputers, which is more important, time or space? Or does it also depend on the purpose? So actually, yes, yung sagot. It actually depends on the purpose. Kasi for a microcomputer, may trade-off yun eh. You can have more components for space and more components for speed. Pero ang magsasuffer dyan is yung cost mo. So if malakas yung processor mo, malaki yung memory mo, mahal yung laptop mo or mahal yung computer mo. So, ayun, depende sa purpose ng microcomputer mo kung ano yung kailangan niyang gawin. So if yung microcomputer mo is nagsusstore ng sensor data, mas important yung space. And if for example yung microcomputer mo is parang siya yung nagko-control, for example, smart farm, nagko-control ng humidity, nagko-control ng temperature, kailangan mabilis mag-adjust. So mas important yung time sa kanya. So mas gagamit ka ng mas mabilis na processors, mas gagamit ka ng mas efficient na algorithms para mapabilis yung kanyang processing. So, ayun. I hope that answers your question. So parang ano rin naman eh. Kung di ba meron tayong mga server na computer. na wala masyadong processing power pero kailangan ng sobrang daming memory. Pero ayun, meron tayong mga computers na ginagamit for editing na gagamit ka na lang ng external hard drive for storage. Parang ganun. So parang trade-off siya ng costs. Kasi if i-try mong isiksik yung both time and space, magmamahal na magmamahal yung inyong device. So, okay, so there's another question. There is no space limitation for the week 4 exercise. So, I think si HackerRank may sarili siyang space limitations. So, sa ngayon, wala pa naman akong nakikitang case na abusado, I suppose, sa memory. So, yeah, as of now, walang case pa na merong limitation sa space complexity sa ating week 4 na challenge. Actually, sa week 3 din naman, walang limitation sa space. So, more on time lang naman. Yeah, pero ayun, alam ko kasi si HackerRank itself meron siyang limit sa space. So, yun lang yung pinaka-limit niya for now. Any other questions? I guess silence means no. Ayun, so if wala nang mga tanong, thank you very much for attending today. Or I guess ni-request nyo rin naman. So, pag naman di kayo nag-attend. Anyway, thank you very much for attending our session for today. Hopefully it helps with your week 3 and week 4 exercises. And ayun, habol tayo guys, week 5. Ayun, good luck and ayun, see you next week siguro. See you next week. Bye-bye.